Okay, well, I'm back. This is going to be our second video or set of two videos on plastics or polymers. Um, and this is sort of the outline of what I'm going to cover across two videos. Mostly structure and chemistry for the first five sort of modules, and that'll be in part one of the video, the first video, and then second video will cover more problem solving with polymer molecular weight and polymer behavior. So there's two main classes of polymers, and some might argue there's a third, but mainly there's two. One group are thermoplastics, and the other group are thermosets. And thermoplastics, they have a lot of chains, and along the chain is this carbon-carbon bond, which is covalent. And then between all the different chains, there's just secondary bonding. So covalent bonding is present along the backbone. And secondary bonding is present between the chains or the backbones. We talk about backbone, that's sort of the structure of the chain. So you've got a bunch of very long, sticky chains that interact with one another. They sometimes get tangled, or sometimes they just have these secondary bonds between them. That's a thermoset. That's a thermoplastic. A thermoset has the same idea where there's covalent bonds along the chains, but then there's also covalent bonds between the chains. That's what this is showing here. These are covalent bonds that attach one chain to another. So covalent bonding is present along the chain or the backbone and between. And secondary bonding it might be present, but it really is inconsequential because there's covalent bonding in the same places, and that's going to merely dominate behavior. All right, so those are the two different classes. Now we'll talk about the two main ways that polymers are synthesized. And for the most part, this would be true for thermoplastics. So the first kind of polymerization is called addition polymerization. It's also called chain growth. Chain growth polymerization. And it's got three steps for the polymerization to take place. First thing that happens is you have these individual monomers, and they get, there's usually a double bond between two carbons, which is transformed into making one end of the molecule have a free radical that's interested in finding another to bond to. Once that happens, then there's just this increasing growth or increasing the length of that chain as each polymer free radical is attached to another. And so the concentration of the monomers just decreases slowly as they get taken up and added to the chain. When that happens, it happens just a couple of chains, and so you have a high molecular weight relatively quick. As opposed to this other kind of polymerization that I'll talk about in a minute, addition polymerization does not have any byproducts. That'll be important when we talk about the other kind of polymerization. in this last step, all of the free radicals end up getting used up and by being added to the chain, and then that ends the growth of the backbone. And the backbone itself then is typically just carbon bonded to carbon, and that's a very strong bond. So these 3 steps look something like this. So I start out with this double bond carbon, and each carbon has 4 bonds, so there's 2 hydrogen there. And one way or another, I break that double bond, and I create a free radical, a place on that molecule that's eager to bond to another, and we get a bunch of these free radicals, and one adding to the other, and you just grow the length of the chain. And so as each of these is taken up onto the chain, the concentration of that monomer decreases. After initiation and then propagation, the reaction ends with termination, when there's no free radicals available for bonding any longer. And so our chain, our backbone, is all carbon-carbon bonds, which are all very strong covalent bonds. So it's difficult to break this molecule back up again. These 2 are semicrystalline because their backbone, their long chain, is simple and kind of easy for chains to line up next to one another. Okay, so there's polypropylene and polyethylene, and then polystyrene, and then we have polyvinyl chloride, or PVC. Here there's just a chlorine at one of these points. This kind of makes it look like the chlorine is just about the same size as a hydrogen. In fact, it's not. This will look, there's my hydrogens, and then there's my chlorine, much larger. And so again, that prevents those chains from lining up with one another and causes PVC more likely to be amorphous. Okay, the next vinyl, or the next addition polymer, is polytetrafluorine, polytetrafluoroethylene. Ethylene because it's just these 2 carbons, and instead of hydrogens, there's fluorine. And this is Teflon. Polyvinyl acetate. Here's my 2 carbon unit. Hydrogen, 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 the way they've drawn it. And this is repeating. And then here they've got this acetate group. So this last carbon is bound to 3 hydrogens. That's a propyl group. And then we've got the carbon double bonded to an oxygen, and then the oxygen between it and the chain itself. So this is a large attachment to the molecule. And that polymer is used a lot with wood glue, white glue, emulsion glue. And then the last addition polymer example is sometimes called plexiglass, polymethyl methacrylate. And so what I've got here, again, basic 2 carbon backbone that's repeating, hydrogen attached twice, and then the CH3 group here. And if this was a hydrogen here, it would be polypropylene, but instead it's a carbon, double bond, oxygen, oxygen, carbon, CH, Polymethyl methacrylate. Looks a lot like polyvinyl acetate, except we've added this CH3 group. I don't want you to think that I expect that you're going to memorize what all of these look like. Instead, I want you to notice some commonalities between all these polymers that are addition polymers. And the most important is that they have at their backbone carbon, 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 carbon bonds. All right, the second kind of polymerization is called condensation polymerization. Sometimes it's called step growth. And for step growth polymerization, the monomers have these functional groups on the ends, and the polymer grows as these functional groups on one molecule reacts with the functional group on the other molecule. And this will make more sense when you see the example. A functional group on one molecule reacts with a functional group on another molecule. So in this case, we don't have molecules that are just gradually being added to the end of a growing chain. We have all of the molecules reacting at the same time. And so the monomers disappear pretty quickly, and the molecular weight goes up pretty quickly as well. The byproduct is a molecule that's simple, like usually hydrogen chloride or water. And one way to make the reaction keep moving in the direction of making more of this polymer is just to keep removing that simple byproduct to cause the tendency for the reaction to continue to move toward making polymer. The functional groups that are binding to one another aren't necessarily carbon. And so this backbone could be carbon and oxygen, could be carbon and nitrogen, it could be carbon and sulfur. These bonds are weaker than the carbon-carbon bond. And the reaction that forms this polymer is reversible. So condensation polymers can be broken down. They could be biodegradable, whereas the addition polymers cannot. So here's some examples of condensation polymerization. This is how polycarbonate is formed. And my functional group here on the one molecule is this alcohol group, and on the other is these chlorine. And so by taking HCl out, I can add this molecule to the other, like here, and create a place for another one of these molecules to attach as well. Or it might be that in space, two other molecules are reacting to one another. It's not one adding at a time to the end of the chain. So that's how polycarbonate is made. Here's polyester. And there are a lot of different polyesters, but in general, I have a diacid, so there's an acid group at both ends, and a dialcohol, there's an OH group at both ends. And I take water out, H2O out, and connect this guy to this. So here is, here, CH2. This is right. This is here, and this is here. And this is in a chemistry class, so don't worry about memorizing this reaction. The polymer that I think you'll most likely work with, like say in industry, that's a condensation polymer, and that has unique characteristics for processing as well as handling is nylon. And so I want to show you how nylon is polymerized. So we've got a diamine, meaning there's two NH2 groups on the end of a length of carbon with its hydrogen. So that's called a diamine. And let's say I've got a certain number of those. We'll say there's N of those. And I have an equal number of diacids. So I've got chlorine, and then a C double bond O. And then I've got my CH2. And then another C double bond O, Cl. It's a diacid. And those two react. Let's say in this chain, there's X is the number of carbons in this chain. And this chain, let's say there's Y as the number of carbons in that chain. And I end up with, now my NH, and then my carbon, CH2, that I had X of, and there's my other nitrogen, and then there's my carbon, and the other CH2. Y of those in a row, and then my C double bond O, and there will be N of those that are created, plus, in this case, H2O. So here's what's important to know about nylon. This byproduct of water, and the fact that this reaction, these two components reacting to form this nylon, is a reversible equilibrium reaction. In other words, it can go in either direction. I could have nylon under certain circumstances and it would break down into the two components if I have water present. Or I have the two components and I form the nylon plus water, and if I pull the water out as I'm making the nylon, then that reaction will just continue to move toward making more nylon. But let's say I've got some nylon that's packaged for shipment, and it's not well dry. And so it's all packaged up, but there's some humidity there. And for whatever reason, I have a lot of heat in this process of moving the product. If I have enough heat in the presence of water and nylon, the reaction can go in the other direction and it decomposes. So that's an important characteristic of condensation polymers, is that you have to be careful to make sure that the reaction can't reverse and you have a breakdown of your polymer. This would never happen with an addition polymer, and that's a benefit of addition polymers. But the addition polymers can't biodegrade. Condensation polymers can biodegrade because the bond is not so strong. In this case, it's a nitrogen carbon bond. The other thing, let's see if I can get a blank. No, I can't. Well, just noting this X and this Y. Nylon will usually have two numbers associated with it, which indicate how many carbons are present in the diamine and how many carbons are present in the diacid. So let's say if this was a chain of 6, and this was a chain of 4, then the diamine has 6 carbons in a row. The diacid has 4 carbons plus these 2, so it also has 6, although we put 4 right here. This nylon then is nylon 6, 6. So nylon 610, the length of this chain would be 8 carbons long, and there would be a total of 10 when we added the two ends. That's how nylon is named. Okay, so we talked about these two kinds of polymerization, and we talked about two classes of polymers. I want to go kind of back and just kind of make some categorize these polymers by exactly what is in the backbone. So we have this group of polymers that have only carbon in the backbone. So these are vinyls. Vinyls are addition polymers. Polyethylene is the simplest polymer. It's a bunch of carbons in a row. And the only thing that's bonded to the carbons is hydrogen. The next more complicated, a little more heavy, a little less likely to crystallize polymer is polypropylene. Again, I've got this carbon-carbon bond repeating in space. I've got hydrogen at 3 of these locations, and at the 4th, I have the CH3 group. That's polypropylene. Polystyrene, we just drew that a moment ago. Looks like that. Here's a monomer that's repeating in space. And each of these carbons on the ring also has a hydrogen. So we've got a much bigger molecule here, which makes polystyrene act very much different. And lastly, we already seen polyvinyl chloride. All of these are hydrogens. But then I've got a chlorine, which is a larger molecule, or sorry, element added on. So these polymers that have just carbon in the backbone are very strong. It's difficult to break those bonds. They don't biodegrade. If we want to recycle, we can grind them up, but they will never sort of self-pulverize. It would never dissolve into the environment. Okay. Another group of polymers are polyesters and polycarbonates. Those are polymers that have oxygen in the backbone. Notice here that the oxygen has 2 bonds instead of 4 like carbon. And so this molecule, this part, and there's my oxygen, and then this part, it can twist and rotate around that oxygen. because it's much more flexible bond than a carbon bond. So it has this ability to do much more deformation, not as in breaking bonds, but as in bending them. Much more of that as compared to the vinyls. It's similar for the next group, which are the polymers that have nitrogen in the backbone. Again, it's carbon that's in the backbone is going to be bonded 4 times, whereas the nitrogen is only bonded 3 times. So this and this can rotate around that nitrogen, allowing that molecule to find or uncoil, depending on whether it's polymerizing and crystallizing or it's being deformed. Okay, so far we've talked about 2 different groups of polymers. One group being thermoplastics, one being thermosets. Thermosets having all covalent bond, and thermoplastics having a mixture of covalent and secondary bonds like polar bonds. And obviously that difference would cause the properties of thermoplastics and thermosets to be different. Some polymers are addition polymers formed that way. Some are condensation polymers. That tends to define their compositions. Those things kind of go hand in hand. And all of that, their composition and how they're formed, affects each of those polymers differently. Their properties, mechanical properties and thermal properties, are a function of what elements are in the backbone, which is a function of how they're synthesized. So we have a lot of different variables on polymers that affect their behavior. Just only thinking about the polymer backbone and its immediate vicinity. If we think a little bit more, step back a bit and think about whether they're branched or how they're branched, then we can see another sort of level of complexity that helps to define properties. So branching is a good one to start with. I've got my polymer, which is 1 mer unit, lots of different molecules long. And it might have other chains that are attached to it that cause it to look branched, right? And it could have little branching, it could have a lot of branching. And depending on the extent of branching will determine a lot about the properties. So is it branched? That determines properties. Is that something that the engineer can change? Probably not. It's much more a function of the chemistry involved in synthesis. But you want to make sure that you understand the extent of branching in the polymer that you're working with. How much branching it is will determine how it arranges itself in space. Another characteristic is when you think about those backbone, I talked about if it was a large R group or a small group. Here's my vinyl. And we talked about polyethylene, where these are all hydrogens. And then we talked about, if you had something larger attached. Let's say I've got just polypropylene. And I have hydrogen here, and here, and here, and then this is my CH3. The next molecule in line, the chemist can put this R group in any of those 4 locations. If the R group is on the other side of the polymer over here, then it's a trans configuration. If the R group is over here, it's a cis configuration. If the attachment is on the first polymer, the first carbon, so that I have one attachment and no break and another attachment, then that's called a head to head configuration. And if I have it on the second, in other words, carbon alone, carbon R group, carbon alone, carbon R group, that's head to tail. So where that R group is attached has a lot of influence on properties. If let's say I have something much longer, or it's much larger, like poly PVC. If I put my chlorine on opposite sides and have a head to tail configuration, everything else is hydrogen, and I alternate sides for this R group, that polymer is going to act much more linear. If I put the R group on the same side, that polymer in 3D space is going to coil. And again, that will have an influence on properties. So we have whether it's covalent bonding throughout or just on the chain. We have, is it just carbon-carbon bonds, or is there something else like oxygen or nitrogen in the backbone? We have, how big is the R group that's attached if it's an addition polymer, a vinyl? We have what side of the molecule, and is it regular in its attachment? If this was regular, we would say it's isotactic, means the same throughout. It could be atactic and be completely random. And all those factors affect the properties of that polymer, but they're not all. So let's just kind of summarize that. So the first thing is 2 groups, all covalent bonds, and covalent backbone only. All covalent bonds, that's my thermoset. Epoxy is a good example. Covalent bonds, that's my thermoplastic. Okay, and then I have, is it all carbon-carbon along the backbone, or do I have oxygen or nitrogen or sulfur in the backbone? These are flexible. These are rigid in space. Then I have branching. And I have R group order. And those have effects on properties. And then, we'll get to in a moment, how large is this polymer? How many molecules long? That's something that is called molecular weight, and that has an effect on the properties. Some of these things are designed by a polymer chemist, and as a polymer, say as a design engineer, you're going to be looking for one thing versus another. All of the structural characteristics, plus now if we start talking about different ways of processing, different ways of manufacturing with the plastic. So we got all of this structure variation or potential variation. If we also add how is this processed, then we come upon another variable in properties, and that's how crystalline is the polymer. So if my polymer chains can arrange themselves to create short range order, then this is what crystallinity is for a polymer. Oops. And so here's a kind of a picture of the crystalline nature of a polymer. So we have this random polymer coil, molecule, long series of molecules. And sometimes within that, every once in a while, the polymer chain will fold on itself to create an order to the molecules in 3D space. A predictable, consistent arrangement of carbon. That's what we mean by crystallinity for a polymer. Nothing like crystallinity in ceramics or metals. This is just some part of the polymer has arranged itself with this short range order. And if it does that, then the molecules have more, the elements, components have more effect on one another. They can resist mechanical and thermal stress better because of that arrangement. And so parts of the polymer will have this arrangement, and it looks kind of like this. So I've got these, the long chains kind of going all different directions, but in some part of the polymer, they're bending back and forth on themselves, and maybe even more than one chain is involved in creating this sort of like a ribbon in 3D space of order among all the carbons. This is really small, 10 to 50,000 angstroms. An angstrom is 10 to the minus 10. So, this is 10 to the minus 6 micrometer in size. Here's an image here. This would be random, amorphous. If the chains could fold back and forth on themselves completely and there was no randomness at all, that would be a crystalline polymer. No such thing exists. If polymers can crystallize, it's something more like this, where call them semi-crystalline. There's a crystalline nature and there's an amorphous nature. Okay, so here's homework number 1. I've got the polymer 1, 2, 3, 4, and 5, and this should be 6. Somehow that didn't come up. These are these numbers refer to 6 different polymers. So I need you to find out what each of these is, use the internet, whatever. Determine by just looking it up whether they're addition or condensation polymers. If you see carbon-carbon bonds throughout, you know that's addition. And then if this is an addition polymer, then it's going to not be biodegradable. If it's a condensation polymer, then it will be biodegradable. Let me know where your hometown is, and then find out, get a list of the polymers, the numbers that curbside recycling is willing to pick up. And that's probably available on the trash or recycle section of the city website. But it's kind of good to know. And then I just want 2 sources for the information that you provide. It could be web pages, it could be an article, a book, whatever. I just want you to have found this information at more than one source. And the point of the exercise is to determine or find out how much does this symbol really mean that it's recyclable or biodegradable, and how much is this really just an identification mark for what kind of polymer it is. Okay, so that is due a week from Thursday. Let's see, that would be the 19th. And you can turn in a hard copy. I always like that, but there will be a way to upload it as well, if that's easier for you. Okay, and this ends part 1 of the polymer video for Thursday, the 12th of October. Take a break, get a drink, or stretch your legs, and then you can try sitting for the second part. Thank you.